Hello and welcome back. For this video, we're going to talk about graphing exponential functions. You can see our goals are recognizing situations modeled by linear or exponential functions, and graph exponential functions showing intercepts and end behavior. We have a few vocabulary here: exponential function, exponential growth function, decay function, and an asymptote. So our first vocabulary here shows an exponential function is a function in the form of y equals a times b to the x. And in this context here, only the b is raised to the x power. So an exponential function is one in which the exponent is the variable, not fixed number. We also have to note that a cannot equal 0, because if I do 0 times any b value, I'll get a 0 as well. Also, we want b to be greater than 0. In other words, it shouldn't be a negative, and it shouldn't be 1. And because if it's 1, any exponent you put on it is always going to output a 1. So some examples here would be y equals 2 times 3 to the x, and the 3 here is the b, and the 2 there is the a. Or simply y equals 4 to the x, or y equals 1/2 to the x. Notice that this 1/2 is still bigger than 0, but it's not negative. Okay, so here we have examples of linear and exponential functions. So on the left-hand side here, the linear function is this one right here. You'll notice it has a constant rate of change. But over here we have exponential on the right-hand side. And if we try to do a constant rate of change, you'll see that the line going up here gets longer and longer each time. So the rate of change is increasing by the same factor. So it's not a constant rate of change, it's some multiple or some factor that's actually changing. All right, so how do we identify exponential behavior? We've got the Richter scale that measures energy that an earthquake releases and assigns a magnitude to it. These orders of magnitude can be approximated by comparing them to the explosive power of TNT. Determine whether the set of data displays exponential behavior. So as the magnitude here goes up from 1 to 2, the amount of TNT increases from 0.6 to 6, which is a factor of 10. So it's going up by 10 times. As it increases from 2 to 3, it's going up by a magnitude of 1 here. The 6 then goes up to 60, which is also again a times 10. Since the change in the output, or the TNT, increases by the same factor, so we're using the same factor of times 10, given an equal change in the magnitude, so I went up by 1, by 1, by 1, the set of data displays exponential behavior. So this is exponential, so times 10, times 10, times 10. Okay, so we're going to try identifying exponential behavior again on this next one. Okay, so in the 19th century, a psychologist created a formula to approximate how quickly people forget information over time. The approximate percentage of newly learned information a person retains over time is shown in the table. Determine whether the data displays exponential behavior or not. All right, so in the table, we started day 0 or time 0, and we increase by 1, and the percentage retained goes from 100 to 80. Well, if I take 80 and I divide it by 100, you'll see that that's 0.8. So it's like they're remembering 80%. And then if I increase from 1 day to 2 days, we are going from 80 to 64. So if I divide that out, 64 over 80. Remember, if it's exponential, it'll have a common multiplier. So 64 divided by 80, and that comes out to 0.8 again. So it's 0.8, 0.8, and then if I go up one more time, I will have another 0.8 multiplier. So this data does display exponential behavior. Okay, so graphing exponential functions. Functions of the form y equals a times b to the x, where a is greater than 0 and b is greater than 1, are called exponential growth. So if I have y equals 2 times 3 to the x, this number right here is greater than 1, so that represents growth. Functions that are in the form of y equals a times b to the x, where a is still greater than 0, however b is somewhere between 0 and 1, in other words, a fraction, are called exponential decay. So if I have y equals 2 to the, let's say, 1/3 raised to the x, since this number right here, the base number is a fraction bigger than 0 but smaller than 1, this represents a decay function. The graphs of exponential functions have an asymptote. The asymptote is a line that the graph approaches. So if I have a graph that looks like this, there's a line down here that the graph appears to approach. That line that's created here is called the asymptote. In most of our equations, that asymptote is actually going to end up being the x-axis down here. All right, we've got some key features. We've got exponential growth on the left and exponential decay on the right. So exponential growth, again, a is greater than 0 and b is bigger than 1. The domain should be all real numbers. The range will be all y values greater than 0. As I said earlier, a growth function for us is going to look something like this. So it's going to approach the x-axis, but it's not going to quite get there, and the x-axis is y equals 0, so we're looking for the values of y greater than 0. Almost always will they have one intercept of y and no x-intercept. The only way you can have an x-intercept here is if you shift this up or down, but you can clearly see there's a y-intercept. As x increases, so as x goes this way, f of x, which is the output, is going up. So as x increases, f of x increases. As x decreases, so as the x go in this direction, the y values are coming down, but they're not going down forever. Remember, they're approaching the x-axis, which is a value of 0. So as x decreases, f of x approaches 0. For an exponential decay, the exponential decay will look something like this. Okay, so we've got a is still greater than 0, but the b value is between 0 and 1, which creates this downward slope to from left to right. Again, I can have all real numbers for the domain, and because I'm still above the x-axis, my graph is entirely above, the range is all values greater than 0. Now, the reason we don't have equal to 0 here is the line gets close to the asymptote, which is the x-axis, but it never actually gets there, never touches that imaginary boundary line. Again, we have one intercept, like we say here, and typically no x-intercepts because it approaches that line but never gets there. The only way we can actually cross the x-axis is if we have some sort of vertical translation in the graph. As x increases, that means as x goes to the right, this graph is getting lower or closer to 0, so f of x approaches 0. As x decreases, meaning we go towards the left, the y values, again, which is f of x, are going to increase forever. So f of x increases or approaches positive infinity. Okay, so here we do have two graphs. This one over here is growth, because as we go from left to right, the graph is increasing. This one over here is decay, because as we go from left to right, the graph is decreasing and it's approaching a value of 0 down here. So it's approaching y equals 0. It's not going to get there, but it's going to get close to it.